Hello, dear learners. Welcome back to our channel. I am Dr. Vanna Yadav from Faculty of Science, the Bhopal School of Social Sciences. And today we are going to start with our another topic, that is molecular orbital theory. In this, we are going to cover first what is the need of molecular orbital theory, introduction of molecular orbital theory, linear combination of atomic orbitals, types of molecular orbitals, key features of molecular orbital theory, order of filling, and last bond order, and we are going to make few MO diagrams. So starting with what was the need of molecular orbital theory. As we were having VSEPR theory, Lewis structures, and many other theories, but what was the need of molecular orbital theory? The earlier theories were not able to explain, basically they were not very much satisfactory in describing the covalent bonding and molecular structures of various molecules. So therefore they were not able to answer the questions like why O2 is paramagnetic in nature, or H2 positive is a stable species, or what is the explanation of electronic spectra. So these were some unanswered questions by VSCPR, valence bond, and Lewis structure. So therefore, there was a need of a new bonding theory, and this is your molecular orbital theory. So Hunts and Mulliken, they developed this molecular orbital theory in 1932, which was able to answer all the unanswered questions of Lewis structures, valence bond theory, and other theories. Now, what is molecular orbital theory? Basically, molecule is the compound formed by combination of atoms. For example, if I combine one H atom with another one, we are forming H2 molecule. So this theory states that atomic orbitals combine to form molecular orbitals. So as you know, when atoms are combining, their atomic orbitals are also combining to give you molecular orbital. And basically molecular orbitals are explained on the basis of linear combination of atomic orbitals, or what we call LCAO. Now, what is LCAO? Before that, what are the conditions for linear combination of atomic orbital? First thing is the energy level, that the orbitals which are combining, they should have what? They should have same energy level. For example, if in case of hydrogen, you can see that it is having 1s1, it is having 1s1, so they are of the same energy. And second condition for combination is presence of same symmetry about the molecular axis, and third one is the proper overlapping between the atomic orbitals. So as you can see, s orbital is spherical and this is another one, so they can easily overlap, show proper overlapping between the atomic orbital. So we have to remember these three conditions before moving on to the linear combination of atomic orbital. First one, same energy, same symmetry, and proper overlapping. Now, when we are forming molecular orbitals, we need to know how many types of molecular orbitals are being formed. So basically, the molecular orbitals are of three types. First one is your bonding molecular orbital. Second one is your anti-bonding molecular orbital, and third one is your non-bonding molecular orbital. So when you are combining atomic orbitals, you are going to form basically two types of molecular orbitals. First one, the bonding molecular orbital. Second one, anti-bonding molecular orbital. And as you can see, what I have shown, that bonding molecular orbitals are comparatively of lower energy in comparison to atomic orbital, and anti-bonding molecular orbitals are comparatively of higher energy in comparison to the parent orbitals. So three types of molecular orbitals are bonding, anti-bonding, and non-bonding. Antibonding being higher energy in comparison to the parent orbital, which is very much clear from the diagram. So now you are clear with molecular orbitals. From the diagram you can also see that molecular orbitals are bonding and anti-bonding. Bonding are formed by constructive interference of wave, because this is solved by Schrodinger wave equation. So bonding molecular orbital are formed by constructive interference, and anti-bonding molecular orbitals are formed by destructive interference. So this is the atomic orbital, combination of atomic orbital. Additive is bonding, which is of lower energy. Subtractive is anti-bonding, which is of higher energy. So it is comparatively lower than atomic orbitals. This is comparatively higher than atomic orbitals. Now moving on to the key features of molecular orbital theory. So first thing which we have to remember is that when we are combining the atomic orbitals, how many molecular orbitals are being formed. So first point to remember is that number of molecular orbitals, the number of molecular orbitals formed is equal to number of atomic orbitals combining. So if you are combining two atomic orbitals, you are going to form two molecular orbitals. If you are going to combine six molecular orbitals, you are going to form same number of molecular orbitals. So normally we have to fill the electron in molecular orbitals. So as you can see, the electrons are filled into the molecular orbital in the increasing order of orbital energy. I'll show you what is the increasing order. And third point to remember is that most effective combination of atomic orbitals occur when they have similar energy. As I have already told you that the condition for combining atomic orbital is same symmetry, same energy and proper overlapping. So now let's have a look at the order of filling. For before that, I'll make a table to explain you how the molecular orbitals are being formed. So if I am combining, this is atomic orbital, this is atomic orbital, this is bonding molecular orbital, this is anti-bonding molecular orbital. So if I am combining 1s with 1s, so as you can see, s and s overlapping is very much effective and they are going to form sigma bond. So the bonding molecular orbital form is sigma 1s and anti-bonding will be anti sigma 1s. Similarly, if we move on to 2s, then 2s combined to give sigma 2s and anti sigma 2s. Now, as you have seen, the order is, then we have 2p. So in 2p we have 2pz, 2px and 2py. So combining 2pz and 2pz, you can see overlapping. This is going to form sigma bonding. So sigma 2pz and anti sigma 2pz. But now x and y are going to form what? They are going to form pi. So pi 2px, anti pi 2px, pi 2py and anti pi 2py. So these are the combination of atomic orbitals and corresponding bonding molecular orbitals and anti-bonding molecular orbitals being formed. Now coming on to how they are going to be filled with electrons. So there is an order based on total number of atomic number present, total number of electron present. So considering atomic number up to 14, we have a particular order of filling the electron, that is sigma 1s, anti sigma 1s, sigma 2s, anti sigma 2s, and then we have pi 2px, pi 2py and sigma 2pz. Then we have anti pi 2px, anti pi 2py and anti sigma 2pz. So in this order we are going to fill the electrons in the molecular orbital. This order is valid till atomic number 14. From atomic number 15 and above, there is a slight variation in this order. What is that? Sigma 1s, anti sigma 1s, sigma 2s, anti sigma 2s, and now sigma 2pz comes to a slightly lower energy level in comparison to pi 2px, pi 2py, and rest all remains at the same level, 2py and anti sigma 2pz. So you can see there is a slight change in the energy as we move on to higher atomic number. So sigma 2pz comes to a kind of lower energy, and pi 2px and pi 2pz, they are degenerate, that is they are at the same energy level. So this is the order of filling of molecular orbitals. Now, points to be remembered while filling the orbitals in this combination. So we have sigma 1s, anti sigma 1s, sigma 2s, anti sigma 2s, and then we have pi 2px, pi 2py, sigma 2pz, and similarly anti-pi 2px, anti-pi 2py, and sigma 2pz. The first one is that in the ground state, electron enters the lower energy molecular orbitals available. So we are going to start filling from sigma 1s, which is the lowest energy, and subsequently we are moving towards the higher energy, high energy. Second thing we have to remember is the Pauli's exclusion principle, that maximum 2 electrons can be contained in a particular molecular orbital. So sigma 1s can have maximum 2 electrons. Similarly, anti sigma can have maximum 2 electrons. Sigma 2s can have 2 electrons. Similarly, this can have 2 electrons according to Pauli's exclusion principle. Moving on to the third rule, which is Hund's rule, that in the ground state, electrons enter degenerate orbitals singly. For example, in case of pi 2px and pi 2py, if I am having two electrons, then first one electron will go to x, then another one will go to y. And if I am further left with some electron, then they will first go to this one and then this one. Then only we'll fill the sigma 2pz orbital. So it is these three principles you have to remember while you are filling the electrons in the molecular orbitals. So from this data, by filling all the electrons, we calculate bond order. Bond order gives us the idea about number of bonds present between those two atoms which are participating to form the molecule. So the formula comes out to be bond order is equal to half of number of bonding electrons, number of anti-bonding electrons. So this I'll show you in the next slide how we are going to calculate bond order. So now starting with the molecular orbital diagram of H2 molecule. So starting with the diagram, first you can see that we have H atom, which is going to form H2 molecule. So 1s1, 1s1, total 2 electrons are going to be present in H2 molecule. Because two atomic orbitals are combining, so they are going to form two molecular orbitals. One will be bonding molecular orbital, another one will be anti-bonding molecular orbital. So this will be sigma 1s, this will be anti-sigma 1s. Now how we are going to represent this in case of MO diagram? So starting with 1s1, this is atomic orbital of 1H atom with 1 electron. Same level we have 1s1 of another H atom. This is atomic orbital, and as I have told you that bonding ones are lower in energy than your parent orbitals. This is sigma 1s, and anti-bonding ones are at higher energy level, which is anti-sigma 1s. Now total electrons present are 2. So both the electrons, as we have already studied the rules, that both the electrons will be present in the lower energy molecular orbital, that is 1s. So MO configuration comes out to be sigma 1s2 and anti sigma 1s0. Calculating bond order, as I told you, number of bonding minus number of anti-bonding upon 2. So we have only 2 electrons. This is 0, this is 2, this is 1. So there is one bond which is existing between 2 H atoms. Another important thing which can be predicted from the molecular orbital diagram is that whether your molecule is diamagnetic or paramagnetic. So just have a look at the number of electrons in molecular orbital. If any of the electron is unpaired, then it becomes, if you have any unpaired electron, then it is your paramagnetic, and if all the electrons are paired in the molecular orbital, then it is diamagnetic. So from the diagram you can see that all the electrons in the molecular orbitals are paired, so it is diamagnetic in nature. So we'll look at one more diagram which is of nitrogen molecule. So from nitrogen molecule we have nitrogen plus nitrogen, which will give you N2 molecule. Nitrogen is having 7, total 14 electrons will be present. So the configuration is 1s2, 2s2, 2p3. Similarly 1s2, 2s2, 2p3. So 1s and 1s, they will combine, 2s and 2s, and then 2p and 2p. So 1s and 2s will form sigma 1s and anti sigma 1s, sigma 2s and anti sigma 2s, and then 2p. You know that 2p is having pz, px and py. So it is going to form pi 2px, pi 2py, which are of same energy level, and then sigma 2pz, and anti bonding will be anti pi 2px and anti pi 2py and anti sigma 2pz. Now how we are going to draw the MO diagram, starting from the lowest energy molecular orbital. So starting from the bottom of your notebook, we are going to form 1s2 of n, then another one 1s2 and 1s2 of another n atom. This is 1, this is 1. So this is sigma 1s and this is anti sigma 1s. So 2 and 2, 4. So starting with 1, 2, 3, 3 and 4. Then we will form 2s2 and we have 2s2, sigma 2s and anti sigma 2s. So 1, 2, 1, 2. Now the difficult part is to make 2p. So starting from 2p, we have 1, 2 and 3. We have 1, 2 and 3. So as I have already shown you the order of filling for 14, that is pi 1 are at comparatively lower energy. So this is your pi 2px and pi 2py, and then at comparatively higher would be sigma 2pz, and then higher anti-bonding. So anti pi 2px, anti pi 2py, and this is anti sigma 2pz. Now you can see 3 electrons are this side, this is 2p3, and 3 electrons are this side, this is 2p3. So total 6 electrons are to be accommodated in your molecular orbital. So starting with 2 degenerate, as you have seen in Hund's rule and Pauli's exclusion principle. First we are going to start with single electron present in both, then still we are left, then we'll do pairing, 4 electrons already occupied, we are still left with 2 electrons and they will be present in sigma 2pz. So we have now the increasing energy order for N2 molecule. if I write the MO configuration, it is sigma 1 s2, anti sigma 1 s2, sigma 2 s2, anti sigma 2 s2, and then as you have seen, pi, the two are at the same energy level, so pi 2px2, pi 2py2, and sigma 2pz2. Rest all are empty. So based on this diagram, we calculate bond order, counting the number of bonding: 2 to 4, 5, 6, 7, 8, 9, 10. So 10 are bonding and 2 and 2, 4 are anti-bonding, divide by 2. So this is your 6 divided by 2, that is 3. So bond order is 3. And talking about the magnetic property, as you can see, all the electrons are paired. So N2 molecule is diamagnetic in nature. So I think from this diagram you are clear how we can draw the hemodiagram for homodiatomic molecules. We have discussed two molecular orbital diagram. They are homodiatomic. Both the atoms are same in nature. Today, in today's lecture, we have discussed homodiatomic molecule, hemodiagram, magnetic property, and how we can calculate bond order. In next lecture, we are going to discuss the heterodiatomic molecular orbital diagram. Till then, happy learning.